What is decimal reduction time, or d-value? There are different types of microbes, and some of them are heat resistant and some are not. We need to kill microbes in food preservation. To increase the shelf life of that food. So first of all, we need to know the time required to decrease the microbial population to a safe limit. So we have to decrease the microbial population uh, to safe limit. So how do we determine it? We determine it by identifying the most heat resistant microbe present in that food. We consider that most heat resistant bacteria as a marker microorganism. Suppose, for example, if we have a pure culture of microbes, say E. coli, and it has the initial population of N naught, and if we have to decrease this initial population to N at, for example, at 90 degrees centigrade, how much time it will take to decrease N naught to N? Uh, can we can calculate this by using the D value. And what is this D value? It is 90% reduction of population. 90% reduction of population, uh, or we can say it is time to reduce the one log cycle. Time reduced to one log cycle. So let us understand this from this graph. This is a semi-log graph between the population n and time t. Suppose, for example, the initial population is 1000. This axis represents the log scale, and this is the normal scale, time 10, 15, 20, and so on. So in this graph we get a straight this curve, and uh, the time required to decrease the population from 1000 to 100, say for example 10 minutes, is D value. So to kill 90% population of E. coli at 90 degrees centigrade, uh, is D value. So here D value is 10 minutes. 10 minutes. It took us 10 minutes to kill 90% population of E. coli at 90 degrees centigrade. Remember, at 90 degrees centigrade, it changes when we change the temperature. So For example, uh, if we increase the temperature, the time will decrease. If we decrease the temperature, the time will increase, and it is vice versa. So here we have decreased the population from 1000 to 100, and this is known as the d-value. This can be 10 minutes, this can be 5 minutes. It depends upon the microorganism and it depends upon the temperature which you have used. So how is it 90%? It is 90%. Let us calculate it. 1000 minus 100 is equivalent to 900. So 900 upon 1000 multiple 100. So this is 90%. This decrease from 1000 to 100 is one log decrease, and also we can say it 90% decrease. So uh, d value is 90% reduction of microbial population at constant temperature. So mathematically we can write this mathematically log n naught, means initial population minus log n final population, is equivalent to t time required divided by d, which is decimal reduction time. Now we can write this also log n naught upon n is equivalent to t divided by d, because log m minus log n is equivalent to log m divided by n. Simple math. Or we can write this as log n divided by n naught. We can reverse it, but negative sign will appear here, is equivalent to t divided by d. Or we can write it as log n divided by n naught is equivalent to minus t divided by d. We have shifted the negative sign from this side to this side. Or we can write this as n divided by n naught is equal to 10 raised power t divided by d. Write this equation, designate this equation as equation first. So now from the first order, now from first order reaction, as we consider the microbial death pattern follows the first order reaction, we consider it. So from the first order reaction, which is mathematically dn divided by dt, time take to change the population n is equivalent to minus k rate constant into n population raised power n. But in first order reaction, this n is equivalent to 1. So we can write this as dn divided by n. Will transfer this n to here, and minus k dt. We have rearranged the terms so that we can integrate it. So now integrate it, dn divided by n from n naught initial population to final population, which will be equivalent to integration of minus k dt from 0 to t Now let's integrate this. This will become ln n naught to n is equivalent to minus k t 0 to t, and this will turn ln n minus ln n naught minus kt. This term will get cancelled because this is 0. Now we can write this as ln n naught n divided by n naught is equal to minus kt. So now multiple both sides with the base of natural logarithm we will get uh, e ln n divided by n naught is equivalent to um, e raised power kt. So but e ln n is equivalent to 1, so we can write n divided by n naught is equivalent to e raised power minus kt. So we have derived this from first order reaction. Let us designate this as true. Now from the equation first uh, and second, we came to know that e raised power kt is equivalent to 10 raised power minus td. If we add both sides ln to the above equation, we will get ln e raised power kt is equal to 10 ln minus td. We know ln e is equal to 1, so we can write this as kt is equivalent to, and this is log n power m, so we will write minus t divided by t ln 10. This is simple math. Here this will cancel out, t will cancel also, so we can write k is equivalent to ln 10 divided by d, or we can write this as 2.303 divided by d. So we get the value of d is equivalent to 2.303 divided by k, rate constant. So this is the decimal reduction time. Decimal reduction time here comes equal to 2.303 divided by k, rate constant. So from the above graph, the slope here, the slope of this curve is uh, k upon 2.303, and d value is inverse of that. Another definition of d value is it is the inverse of the slope. If k divided by 2.30 is the slope of this curve, the d value is inverse of that, that is 2.303 divided by k. Hope you understood this. Thank you for watching.